I'm very happy to introduce the next speaker. He's a colleague of mine, Pawan Goyal. Pawan got his PhD in 2018 at the Otto von Guericke University in Magdeburg, and since then is a postdoc in the CSC group at MPI, Max Planck Institute here in Magdeburg, headed by Peter Banner. He also got an honorable mention at the last Householder for his PhD thesis, and today is going to talk about data-driven identification of port-Hamiltonian system. Please, Pawan.
Thank you very much, David, for your introductions, and also thank you, organizer, for giving me an opportunity to present one of our latest work on port-Hamiltonian systems. And this is joint work with Peter Banner and Paul von Duren. And so today I'm presenting, as I said, on the port-Hamiltonian systems, and there has been quite some interest in the community in the port-Hamiltonian systems and the various aspects of it. And so today I will be also a little bit presenting about our work on port-Hamiltonian systems. Okay, so I begin with a little bit of the basics of linear dynamical systems. So just to a quick recap of linear dynamical systems, and so I focus on linear dynamical systems on this form, which are like classical state space form of linear systems, where X is a state, U is a control, and Y is output, which you want to measure it. And one of the when you start doing modeling of any process or dynamical process, this is the one of the first step which you want to look at, and this kind of systems appears while you want to model a process with using the first principles, and sometimes if you have a non-linear dynamical system, you want to linearize about the steady state or equilibrium, and then we can have a linear approximation of the linear systems as linear systems. And this kind of system has been studied a lot in the last decades and even centuries, I would say. But in this talk, I will be more to focus on the data science kind of world where we want to construct linear dynamical system from the data. And in the last couple of decades, there has been a very much advancements in the measurement technology, in the sensors, so which allows us to get very good and accurate data sets from the enormous amount. And therefore, we are interested in constructing linear dynamical system directly from the data without going into first principle modeling. And there are quite some advantages to construct models directly from the data. And one thing which is kind of advantageous is that we don't need to know the first principle laws for the process. And also we don't need to know exact parameters which are can be used by the system. For example, in flow problems, the Reynolds number or densities, which we may not know accurately, and we rather can estimate or can get a model directly using the data which we can get using the sensors, for instance. And in this talk, we are interested in constructing dynamical systems directly from the data. And this kind of field has been studied quite by the various people in the last centuries, giving the input-output mapping. We want to construct underlying dynamical systems. And there are some references going back from the 1990s. There are books where they have illustrated various aspects or various concepts to construct linear dynamical systems. And I'm not going to go all these approaches, but for this talk and in this talk, what we'll focus on is Lovner approach. This was proposed by Mayo-Antoulas in 2007. And what is nice about this approach is that we only need the frequency response, and we're trying to construct underlying dynamical system directly using the data. And one of the main ingredients for the Lovner approach is the frequency response and the transfer functions measurements of the system. So just to quickly recap, what is it, transfer functions, people who are not familiar with it. So transfer function is a given dynamical system instead of time, we transform the system in the frequency domain using the Laplace transform. So you have the state x of t, which is mapped to in the frequency domain by using the Laplace transform, and then you have x of s, and the derivative becomes the s times x of s. Then you apply Laplace transform on the first equations, then you get the systems like this, and which actually will give you input-output mapping y of s to u of s, y at transfer functions. And this is kind of this quantity h of s, we say, and the transfer functions, which actually transform input in the frequency domain to output in the frequency domain. And one of the good thing about this kind of mapping in the frequency domain is it's a linear mapping. And so as we know, in the convolution in the time, and if you take the Laplace, go into frequency domain, which will convert convolution into product as a linear systems. So this h of x, which we call as a transfer function, is a very important quantity for linear dynamical systems, and which actually capture a lot of information about your systems, like stabilities is one of the things which you can understand directly from the transfer functions. So, and there are various methods in the literatures and in the experiments how you can measure this quantity. And one of the things is like you can excite your systems and you observe the vibrations, and by using the simple signal processing, you can get these measurements directly in an experiment. So far we have these transfer functions, and the transfer function, one of the good thing is that this transfer function h of x, they are rational functions. And if you want to identify underlying dynamical systems, then what we can do is that we can cast this problem as a rational interpolation problem. And so what is a rational interpolation problem? Just to recap, is that given measurement points, so interpolation points, sigmas, and the value at the interpolation points, let's denote by gammas, then what we want to construct is a transfer functions, realizations, which interpolates your measurements. And this problem also has been studied a lot, and there are various approaches to construct these rational approximations. And as I said, what we are looking at to learn a kind of framework, which is also trying to solve rational interpolation problems. So what is Lovelock framework in a nutshell is that given a data sets, so sigma and the mu at the samples. So this is what we need in order to apply Lovelock framework. And at the first step, what we do is split the data into left and right partition. So it's just pick the subset. So there are two L data points. We make two sets of L and L points. And then we try to solve this rational interpolation problems in such a way that it interpolates the data sets. So to go forward with this, so what we do is we simply put this data lambda as in mu's in the diagonal form, and then the vi and wi as vectors. So we just rearrange the data set, which will allows us to construct the two matrices, Lovener and Shifter-Lovener matrices, which are the solution of these Sylvester equations. Then the rational functions, and if you have C, E, A, B, C matrices, and if you construct that like this, which are directly from the Lovener and Shifter-Lovener, and V and W are directly the data sets, then you actually solve these interpolation problems. So at the moment, this directly constructed from the data, and your rational functions or dynamical system can be obtained directly using the data sets. So here, in order to solve the Shifter-Lovener and Shifter-Lovener matrices, there is a Sylvester equations, but you don't need to solve the Sylvester equation, but rather they have analytical expressions in terms of divide and difference form, and you can directly compute these matrices without any computations. And the rank of Lovener matrix also will tell you minimal order of realization, which is a minimal order of the system which can represent your data sets. And if you have more data than the required to represent your dynamical systems, then there is a compression step which you can perform to reduce your reduce your dimension of your dynamical systems. So this is a kind of like an approach which directly gives you a dynamical systems which interpolates your data sets and without almost no computation cost. So there are a lot of advantages of Lemma approach. One thing is like it readily gives your rational approximation and interpolates your data sets, which we have seen it, and is easy to implement. It also can tell you what is the minimal order of realization which you need in order to capture or interpolate your data sets. And it has been successfully applied in the various worlds. And this is, I think you can look at any of the talk from the Mayo-Antoulas, and then he has very nice applications where he shows the various application of Lemma framework in the various fields. However, so one of the disadvantages or limitation of this approach is that if you want to get any rational approximation, then it's fine. But as soon as you start imposing any kind of a structure which you want to have it, then it is hard to apply it. So this structure can be any of the structures. So this can be delay, second order systems, and although there has been some variants of Lemma framework with some modification which allows us to preserve the structures, but you have to do some kind of modification in order to apply the Lemma framework. And in this talk, what we are particularly interested in is in the passive systems. And the passive systems are like, there are a lot of engineering systems which are passive, and in the communities in the numerical linear algebras, the passive system and port-Hamiltonian systems in the last decade has like grown a lot of attentions. And so what is the passive systems? So, and why they are becoming so popular in our communities is, so let's focus on the passive systems. And the passive systems are, one can think of energy-based modelings. And most of the systems, what we have is can be models based on the energies. And one of the key ingredients of the energy-based modeling is a supply rate, which is kind of, you can think of given in terms of the input and the output. And this quantity explains the exchange of the energies with the environment via input to output of the system. So this is you can model a lot of engineering processes via the energy-based modeling. And passive systems are also this energy-based modeling, one can see of it, where the supply rate is given by the inner product of input and output. And passive systems are passive dissipative systems. That means that these kind of systems cannot generate the energy by itself. And that means this quantity supply rate, which is kind of dissipative, will be always greater than equal to 0. And there are also some properties that these kind of passive systems, the energy which it can store, the maximum energy it can store, it can be given in terms of the state in which the system is at the moment. And this L of X, this internal energy, the quantity, how you measure it, is also can be, this quantity can also be used to say the Lyapunov stability of the passive systems. And as I said, these kind of systems cannot generate any kind of internal energies, and these passive systems are also asymptotically stable. So they are like a lot of various properties and which passive system possesses, and you want to keep this kind of nice property which you directly get from the modeling. So how do you really check for the passivity of a system? So let's say that you have a given realization A, B, C, and D, and it is a proper transfer function h of x, and the system is strictly passive if the transfer function is positive real. That means this quantity is always greater than equal to 0, and the system is stable. This is one of the criteria how you can check for the passivity of the system. And the other very well known is in the Kyp lemma. So let's say that you have A, B, C, D systems, and it's of the minimum realization. And let's denote this quantity, the matrix WQ of this form. So you assemble these things. Then the system is passive if and only if there exists at least one Q which satisfies these inequalities. And the system is strictly passive if this is strictly greater than equal to 0. And So this is how you can check by Kyp lemma that if the system is passive or not passive. And one of the realization of the passive system is a port-Hamiltonian system, which also has a lot of nice properties. And every passive systems can be written as a port-Hamiltonian systems, or it has a port-Hamiltonian realization, which is this form. And if you have this J, R, Q, all the matrices has a very nice properties. And one of the properties which you can see here is this: if you put these matrices in this block form, then they satisfy this skew symmetric or positive semi-definiteness of the matrices. And this Q matrix also has a nice property, because once you have this port-Hamiltonian realization, then the Q also you can use to characterize the Lyapunov stability of the systems. So it has a lot of nice properties, as I mentioned it. And what we are interested in to have this port-Hamiltonian structure in our modeling. So as I said in the beginning, our interest lies in identifying this port-Hamiltonian realization only using the data. So only given the input-output mapping, we want to construct these port-Hamiltonian realizations. And it is a linear system, so you can cast this problem as a rational interpolation problems, but you have a lot of constraints, what we have seen it here. For example, this skew symmetric properties of this matrix and the positive semi-definite of this matrix. So still it is a rational interpolation problem. One can ideally solve with the Lyapunov framework, but it is a constrained one. So, but we want to solve this problem, we're using the Lyapunov framework. So look at again the Lyapunov framework, as you know, is that we only need these data sets, sigma and yk, and we still follow the standard procedure for Lyapunov. So split the data, and then the problem which we want to solve is that rational functions h of x, rational interpolation problem, which will interpolate your data sets, but we have the port-Hamiltonian structure, which we want to keep in our matrices. So what we do is at the first step again, that let's organize the data sets in this way, which we'll do. And what we have done in the classical Lyapunov framework as well. And then if you put the Lyapunov framework in the matrix form, you have the Salvestri equation which solve for this Lyapunov matrix and shifted Lyapunov matrix, and which will interpolate your data sets. But if you do in a regular way, what we know, for any given choice of interpolation points, it will not keep the port-Hamiltonian structure in your linear systems. It can give you interpolatory model, but it will not have a port-Hamiltonian structures. So an approach which was proposed by the BT, and he presented this year, beginning of this year in ISOMS. So trying to find a passivity certificate by solving Kyp lemma and trying to do state space transformation, which will lead to a port-Hamiltonian realization. But we have to solve this Kyp lemma, which might be expensive if you don't have the low dimensional system. So can we do something about it? So can we make a clever choice of interpolation point that will lead port-Hamiltonian system by construction? So without any computational cost, can we get by applying classical Lyapunov to get a still port-Hamiltonian realization? And the answer is yes. That's why I'm presenting today here. And the answer lies in the spectral zeros of the systems. And this was the work which we published this year, in the beginning of this year. And so the spectral zeros of the systems is which solves this kind of eigenvalue problem. So these are the definition of spectral zeros. And the thing is that if you choose your right interpolation point as a spectral zeros that lies in the right half plane, so you choose your interpolation points on the spectral zeros. So that means you will get this kind of interpolatory conditions, and you choose the left interpolation points and condition that are the conjugate of this. So you have the left interpolation conditions directly coming also on the spectral zeros, but on the left half plane. So this is how you split your data set. So you choose this interpolation point as a spectral zeros. And then let's define this lambda, which contains the right half, the spectral zeros that lies on the right half plane, and the measurements in the W. Then if you put the data set in this framework and apply classical Lovener framework, then the Lovener matrices and the shifted Lovener matrices which solves these equations. These are also like kind of Sylvester equations, but what you can see is that the Lovener matrix and the shifted Lovener matrix, again, you can give analytically, you don't have to solve this Sylvester equation. They are very structured and this have analytical form in the divide and difference form. And the key thing which you can see here is that this Lovener matrix by construction is a Hermitian, and the shifted Lovener matrix is a screw Hermitian. And this is, if you choose your interpolation point on the spectral zeros, it comes by the constructions that this has these properties of being the symmetric, the Hermitian and the screw Hermitians. And then the realizations you can give in this form. So directly your realizations will be given directly in the Lovener and the shifted Lovener framework. And that realization will be passive, and the port-Hamiltonian form if the L is positive semi-definite. And as I said, this will be directly by the constructions will be passive, and if you choose your interpolation point at the spectral zeros. One of the advantages of this approach is there is no LMIs involved. So, and this gives by constructions the port-Hamiltonian realization. And in this talk, I'm not going through multi-input, multi-output systems. These all the things which are presented so far is only single input, single output systems, but one can use of tangential interpolation ideas, and where the directions will be the zero direction corresponding to spectral zeros. So one of the main challenge to apply so far this method is that we need spectral zeros, and the spectral zeros depends on the realizations, which we don't have a priori, and we also don't know where the spectral zero will be lying, because classically when we identify linear systems, we can only measure the transfer function on the j omega axis, but the spectral zeros can lie anywhere in the complex plane. And as I said, the spectral zero will also depends on the realization, which we don't know. So even though you have a spectral zeros, which you might know, let's say, but even then, it is very hard to approximate or estimate the transfer function at the spectral zeros in an experiment, because generally you have very nice properties to estimate the transfer function on the j omega axis, but not at any given points in the complex plane. So this still remains the challenge if you want to approximate or identify the systems solely from the data given on the j omega axis. So as a remedy, what we do is we collect the samples on the j omega axis and apply classical Lovener to construct a minimum realizations. And we use that minimum realization to estimate the spectral zeros and the zero directions. And then we use this model to get a port-Hamiltonian realization underlying, which will approximate your data sets, which you get in an experiment. So this is how this in the nutshell. If you have the samples on the j omega axis, you can do an intermediate step to construct a Lovener framework to estimate the spectral zeros and zero directions, and then apply port-Hamiltonian algorithms or identification so that you can get a port-Hamiltonian realization. So let's see how it works. So what we have is a RLC circuit, and this RLC circuit is only 5 by 5. It's a very small RLC circuit, but as we can see, this is not in the port-Hamiltonian form, although the system is passive. So let's say we want to construct a port-Hamiltonian realization. Of course, you can apply Kyp Lemma and then do the state space transformation. But assuming that we don't have the access of, or we don't know how to solve LMIs, or we cannot solve the LMIs, then what we can do, let's take 20 frequency response data points on the j omega axis and apply classical Lovener. And when we apply classical Lovener, then we see after 5, there is a sharp decay, it's almost a machine precision. And that it also tells that the underlying dynamical system is minimal order is order 5. Then we construct a Lovener model from it. And then what we see is that spectral zeros, when we compute spectral zeros from the original system and the intermediate Lovener models, then we see they are exactly on top of each other. And then we can estimate our spectral zeros and directions and can identify the port-Hamiltonian realization. And when we do this one, then we can actually get this port-Hamiltonian matrices. So this number are there, but I just wanted to show that there is in all the port-Hamiltonian matrices, all the matrices which can characterize the port-Hamiltonian realization. And if you compare these two realizations, they are exactly on top of each other, but one is having the port-Hamiltonian structures, another one doesn't have a port-Hamiltonian structure. So let's go a little bit larger RLC circuits. So here we have a larger RLC circuits, but we don't know from where the data comes, but we are given 200 frequency response data points between the range in these frequencies. And we want to construct an underlying port-Hamiltonian which can interpolate these 200 frequency data points. So what we can do as a first step, apply classical Lovener and observe the decay of single values, which can tell us what is the minimal order of the systems or what is a good order of the system which can interpolate your 200 frequency data points. So what we do is we just construct two low order models, which are order 2 and 14. And then we can approximate for order 2 and 14 the spectral zeros and the directions. So this is what we get it. So in the blue, which you see in the original spectral zeros, and in the green, this is order 2, and in the magenta, you see the order 14. And what you see, interestingly, is the spectral zeros are quite different than original systems. But when you construct a port-Hamiltonian realization and compare how close the realizations are, for order 2, we still can approximate very well, but order 14, you see, is almost order 10 to the power minus 10 order. So, and these are both of them are the port-Hamiltonian realization, which can approximately interpolating your data sets. So to conclude my talk, what I presented is the concept of passive systems and identification of port-Hamiltonian realization using the data set. And in particularly, what I have shown is how if the data sets are given on the j omega axis, which is the most often in the practice which we obtain, and how to determine underlying port-Hamiltonian realization. And they are what we have seen, this extension of classical Lovener framework, and by clever choice of interpolation points, which we can construct port-Hamiltonian realizations directly by constructions. What is ongoing work, what we have seen is that we have found at least one port-Hamiltonian realization that is passive, of which represent your data set, but there are many port-Hamiltonian realizations. So we are looking at how to find the realization which has the maximum passivity radius, and the passivity radius determines how robust the system or the port-Hamiltonian realization
So it seems that Pawan had some problem with the connection just at the end of his talk. Let's see if we can reach out. Probably trying to connect I'm sorry for that. Okay, so let's do that. Yeah, I'm sorry for Pavan. I will say that we can connect together shortly. Okay, it's back.
Okay, I'm sorry, there was some disturbance in the internet, and okay.
Okay, if you want to finish your talk.
I don't know where I was actually.
We were drawing some conclusions.
Okay, I'm sorry. So,
Fine.
so just to conclude again, so in this talk, I don't know where I missed all of you, but as David has said, I missed in the conclusion, so I present again.
Sorry, maybe you want to share the screen again? Okay.
Here we go. Sorry again for the disturbance. So in this talk, I have presented the concept of passive system and how we can identify the port-Hamiltonian underlying systems or realization using the data. And what we have extended is Lerner approach, where with a clever choice of interpolation point, which are spectral zeros, you can readily get port-Hamiltonian realization of the systems. And what we are currently looking is that to find a port-Hamiltonian system which has a maximum passivity radius, as if a passive system can have many port-Hamiltonian realizations, but we are looking to find the one which has a maximum passivity radius, so that is more robust to the passivity. And we are also currently looking to extend this other framework for the second order passive systems. And we don't want to write in the first order companion form, but rather we want to have the second order systems, and which comes in the mechanical systems. And with this, I would like to thank you for your attention. And there are some references here for the talk. Thank you very much.
Thank you very much. Pavan, any question from Zoom? Usam?
So there's a comment by Sergei Dolgov. So he thanked you for the talk. Sorry if I missed that. What is the data that you observe? Is the interpolation sensitive to noise in the data?
So thank you, Sagar, for the question. So what we observe is, if I can go quickly to the frequency response, which is h of s, basically. So it's in the beginning of my talk. So what we measure is h of s, and which you can measure in an experiment, basically. And yes, the approach is slightly sensitive to the noise. And at the moment, like if you collect a lot of data sets, then if you don't truncate your decay of singular values of the Lerner framework at the machine prism, but it can depend on what kind of noise you have and what is the level of the noise you can truncate before, which generally gives you good results. But we are looking into more, like let's say, in the more clever way to handle the noise in the data sets.
Okay. Any other questions, Usam?
Well, there is just a remark by Bo Kekstrom. The reference Leonard should be L. Young, L-J-U-N-G.
Okay. Okay, thank you.
I guess that's all.
Okay, Jemima from YouTube?
No questions from YouTube.
Okay, so thank you again, Pavan, and for more questions, we invite you to join us on Gather shortly.
Actually,
and